Thank you. Again, today's meeting is about the fundamentals of thermal displacement ventilation, and we're very excited for it this month. Coming up, perfect. As always, we are a volunteer organization and we can always use more hands. If you have any desire or open time and would like to volunteer or come out and help out the local chapter, please shoot me an email or get a hold of us at any of the board members. We would love to chat with you and love to tell you what's open and available for volunteering. Upcoming events next month, we've got a YEA happy hour with some bowling, February 16th at the garage from 3:30 to 5 p.m. That will be on our events calendar, and more information can be found there if anybody is interested. Today, we are joined for this topic by Dr. Livchak. He has been nice enough to give us some of his time to be able to talk about this meeting. Dr. Livchak has over 30 years of international experience in the HVAC industry, graduated from Moscow Civil Engineering University in 1983, and then has also got his Ph.D. In 1989 from the same university. He covers several areas, including air distribution, heat recovery, cooling, and heating systems, as well as acoustics and commercial kitchen ventilation. Dr. Livchak, I'll let you kind of continue from that, but obviously really appreciate your time, and I will quit sharing and then let you take over anything that I may have missed.
Thank you for the introduction, Amin. Let me share my screen.
Perfect. That does show the notes on it.
Okay.
If that matters for you.
Swap. And I need to somehow remove this, right?
Perfect.
Right. Can everyone hear me okay? Amin?
Yes, we can hear you.
You're good. You're good to go.
All right. Hello, everyone. The subject of presentation today is fundamentals of thermal displacement ventilation. I'll go through a few introductory slides first. First of all, as part of Distinguished Lecturer Program, we do it. This is a volunteer program. We travel, we do presentations online as well. What is very important that you rate our presentation. That's how we evaluate it, and that's the only way how we could improve the program. These are introductory slides. I encourage everyone to actively participate in ASHRAE activities, local chapters, as well as the annual meetings. We have two meetings, actually, summer meeting and winter meeting. Winter meeting is coming in a few weeks. It will be in Atlanta. This presentation is credited for one educational hour. And I'll go straight to the learning objectives. After this presentation, you should be able to classify air distribution strategies as function of thermal stratification in the space and describe thermal displacement ventilation performance in cooling mode. You should be able to apply ASHRAE Standard 62.1 in thermal displacement ventilation system design. Describe benefits and limitations of thermal displacement ventilation, and also learn how displacement ventilation can be used to reduce risk of airborne infection in a restaurant environment. I mean, I don't see any questions, but at any time when you see the questions on the screen, please feel free to interrupt me and ask a question. All right. First of all, from ASHRAE fundamentals, I'm showing this picture to explain how mixing ventilation differ from stratified systems. So to classify all types of air distribution systems, there are fully stratified system, partially stratified, and fully mixed systems. And here you can see the temperature profile. On the left chart, you can see fully stratified system. This is thermal displaced ventilation, where temperature profile in cooling mode is having lower temperature in the lower part of the space and higher temperature in the higher part of the space. We have partially mixed systems. These are systems with underfloor distribution, and depending on throw length of floor diffusers, it could be mixed less and it could be mixed at a higher rate. And fully mixed systems, these are typically mixing systems. They are characterized by uniform temperature stratification throughout the space. First of all, we're all familiar with mixing systems. So these are, as you can see on this picture, this is a typical ceiling four-way diffuser. Objective of mixing system is to mix supply air with room air as fast as possible and provide uniform temperature and contaminant conditions in the space. Typical supply temperature is about 55 degrees Fahrenheit. Contaminants are diluted and mixed within the space. With thermal displacement ventilation, I would emphasize again, so this system works only in cooling mode. We know that cold air is more dense than warm air, so it's heavier than warm air. And displacement diffusers are typically located in the occupied zone, and cold air supplied from displacement diffuser is cascading towards the floor, falls down, creates kind of small waterfall, and then heat sources in the space carry this air into the upper part of the space. So every single person in the room would work as a small fan, basically warming up the air and moving the air from the lower part of the space to the upper part of the space. Contaminants that are neutrally buoyant also carried into the upper part of the space. As a result, we don't have uniform temperature in the space. We would have lower temperature in the occupied part of the space and high temperature near the ceiling. Principle of displacement ventilation is very well known. So Native Americans actually use it in teepees. For example, you can see that there is a teepee. There are usually ventilation openings in the perimeter at the lower part of the space and fire in the middle of the space. And this fire moves the air from the lower part of the space into the upper part of the space. So this ventilation principle is ancient. It's used in medieval castles in Europe, in churches. So this is pretty well-known principle. On this slide, we see CFD simulation. This is computational fluid dynamics. It shows displacement ventilation as it was tested in laboratory. We see half of the space. These cylinders, they represent, we call them dummies. They represent heat sources, equivalent in heat source as a human body. It's about 100-watt light bulb inside. Diffuser are shown like half of diffuser in here. And we can see how air propagating from this diffuser first, it cascades towards the floor because cold air is heavier than room air. Spreads evenly throughout the space. And eventually you will see how these cylinders would be warming up this air and eventually creating the plumes of warm air rising into the upper part of the space. And in just a few moments, you will see also temperature profile in the space. So these are ceiling lights. They also represent the heat source. And you can see how gradually all this air, first it spreads along the floor, and then heat sources move it into the upper part of the space. eventually supply air, which is exhaust. And here is the temperature profile in the space. We can see that green and blue colors represent cooler temperature, and red and yellow represents warmer temperature. We can see that there is a lower temperature in the lower part of the space. We call it occupied zone, and higher temperature in the upper part of the space. This is how it looks in a typical building. Displacement ventilation is very efficient for temperatures with a high ceiling. Effectively, we need to cool only the lower part of the space and allow temperature to stratify into upper part of the space. This is typical temperature profile in the occupied zone, and as we call it shift zone, that's above the shift zone, the air is fully mixed, and it's much warmer than air in the occupied zone. It stays stratified in the upper part of the space. It's very easy to calculate mixing system to calculate airflow and temperature required to deal with the heat load in the space. With displacement ventilation, we always need to solve for exhaust temperature or temperature in the upper part of the space. And there are two methods used to calculate thermal displacement ventilation: temperature-based method and shift zone method. Temperature-based method is designed for heat removal, and it requires a lot of information about the heat sources in the space. So we need to know location of the heat source, and also we need to know what portion of the heat is released by the heat source by convection and by radiation. And based on this location and these parameters, we can calculate what is the exhaust temperature. Exhaust temperature is always higher than temperature in the occupied zone. And when we need to solve for more involved method is shift zone, and it's used for thermal comfort and also contaminant removal in the space. It is a much more intensive method to do the calculation. It calculates plumes from each heat source, depending on the size of the heat source and location of it in the space. It makes sure that we maintain the shift zone above the occupied zone. So all the contaminants are stratified into unoccupied zone, above the occupied zone, and not recirculated back in the space. And for this method also, there are empirical methods, but also we would recommend to use CFD modeling to calculate displacement ventilation utilizing shift zone principle. Any questions so far? All right.
None through on the chat yet.
Okay. How many people do we have?
We've got 11 with us at the moment. We've got some still coming in though.
You can see, you can find this book in ASHRAE library. There is a system design guide, how to calculate displacement ventilation. And now I'm going to talk about the applications. So first applications of thermal displacement ventilation were in schools, and especially northern part of the US. Well, first it was, first displacement ventilation actually was introduced in Scandinavia, in Nordic countries. And roughly in the early 90s, it was, we started using it in the US market as well, US and Canada. So here you can see the displacement diffuser in the corner of the space. It works well in the classroom environment. It provides better indoor air quality. It allows to use more of outdoor air without energy penalty. And diffusers are pretty quiet because you need to provide large air distribution phase. They're pretty quiet and provide draftless environment in the space. This study was used in classroom as well. What you can see here is carbon dioxide concentration in the classroom along the whole day. So we can see yellow is the CO2 measured in exhaust, magenta is in supply, and the blue color shows the CO concentration in the room, measured in the room, in the classroom. You can see that class starts around 7 a.m. We can see how CO2 stratifies. So we have low concentration in supply naturally, higher concentration in classroom itself, and even higher concentration in exhaust. So we can see that CO2 stratifies in the room, providing better indoor air quality with actually the same amount of supply air. Here you can see side-by-side comparison. Again, CFD simulation. On the left side, you can see how the plume of exhaled air spreads in a displacement ventilation environment, and on the right side, how it spreads with mixing ventilation. In both systems, supply airflow is the same, but the only difference that with displacement ventilation, we can supply air at high temperature compared to mixing system. Again, looking at on the left on displacement, we can see how this warm air exhaled from students is stratifying upwards with displacement. And if we look at mixing system with ceiling diffusers, four-way ceiling diffusers at the ceiling level, we can see how this supply air basically pushes all the contaminants associated with exhaled air downwards in the occupied zone, and eventually all the contaminants are mixed within the occupied zone. On this slide, you can see side-by-side comparison, CO2 concentration in classroom on the left side with displacement, and on the right side with mixing system. Again, you can see that in the occupied zone, you have a low concentration of CO2 compared to mixing system. I'm very much involved in this development of commercial kitchen ventilation and ventilation of restaurants, so I'll say a few words about applications of displacement ventilation in this environment. First of all, when we speak about kitchens, it is very important to understand that air distribution system plays significant role in hoods capturing containment, because hoods installed above cooking equipment, plume above cooking equipment is fairly lazy. It develops with very slow velocity, and any cross draft movement above cooking surface may create this plume to spill. Very easy to explain it. You can see the strong guy trying to blow the candle by sucking it off, and he's not successful, but even a child can blow off the candle when he's blown on it. So that's the same principle how air distribution works in the kitchen environment as well. So you don't want to create any drafts in the kitchen. Again, I'm going to show you comparison mixing versus displacement ventilation in a kitchen environment. What we can see here, we have a typical quick service restaurant kitchen. We have fryers and broiler, hood above them, island with heat producing equipment, mixing system with four-way diffuser on the left side, on the left picture, and displacement ventilation on the right side. You may be asking why we have displacement diffuser at the ceiling level here, and the explanation is very simple. The floor space in kitchen is at premium, and we've placed displacement diffusers near the ceiling here, but still it provides displacement effect because cold air cascades from this displacement diffuser towards the floor, then spreads in the occupied zone and being carried in the upper part with heat producing cooking equipment. Again, let's take a look at air movement in the space. We can see air supplied from four-way diffusers. These four-way diffusers actually blows the air onto cooking surface and creates some problem with the spillage from this hood. So this hood would need to operate at higher airflow to compensate for this cross draft created by diffuser. But as we can see that air is supplied at high velocity and spread through the whole space. With displacement ventilation, we can see air is coming from displacement diffuser. It cascades towards the floor, almost like working like a waterfall. First, filling the lower part of the space with fresh, cool air. And then eventually we can see how heat sources move the heat into the upper part of the space and in the hood. No cross drafts across the hood area. So that allows actually the hood to operate at lower exhaust airflow rate. On the next slide, we'll look at temperature profiles in the space. Stop the picture at about the same spot. Oops. Again, on the left side, we can see system with mixing. We are looking at temperature profile of the space. And we can see that mixing system does its job. It provides fairly uniform mixing in the space, and temperature throughout the space is fairly uniform. With displacement, we can see that there is a lower temperature in the occupied zone and high temperature in the upper part of the space. Again, in these two cases, supply air temperature, supply airflow is exactly the same in both cases. And we can see that just changing the air distribution method using displacement ventilation in kitchen environment, we can reduce the temperature in the occupied zone by 5 to 10 degrees Fahrenheit. Another important benefit of displacement ventilation, as I showed in classroom environment, and it also applies to dining rooms, that displacement ventilation prevents airborne contaminants from spreading. Few words about COVID. First, with the first cases originated, when first cases were analyzed, everyone was thinking that COVID is spread only by contact. And World Health Organization was neglecting the fact that the bacteria can spread, virus can spread via airborne contaminants. And first documented case was a restaurant in China. It was showing there was one sick person having a family dinner in the restaurant, and they traced how their virus spread. First, members of the family were sick, but then they also traced this to people sitting at the table C and B that could not be contributed to contact. So that actually proved the case that the virus, COVID virus, is spreading by airborne path, and that ventilation, in this case it was mixing system blowing the air from the side of the window, plus there was very little amount of outside air supplied into this restaurant. It basically was the source of contamination. Air distribution and ventilation system was the source of contamination for people sitting at the table B and C. And that's where it was concluded that droplet transmission was promoted by air conditioned ventilation. This is a very well documented case. Speaking of restaurant ventilation, so we're thinking actually how we could localize contaminants in the space, and that's where, again, thermal displacement ventilation principles could be used. If we think about the restaurant, the booth, we could supply fresh air under the sitting area and have local exhaust above the table, and that would minimize spread of contaminants, would look like shown on this picture. So that would be a good method to minimize spread of airborne contaminants across dining area. In summary, benefits of thermal displacement ventilation kitchens. It's a unique system because it allows improving indoor environmental quality and also saves energy at the same time. As I mentioned, we can achieve lower temperature in the occupied zone with the same temperature, or if we shoot for the same temperature, in both cases, we could increase supply air temperature. For example, in classroom environments, we could achieve, there was a study conducted in California. We compared mixing and displacement systems, and we concluded that we can achieve the same temperature conditions in the occupied zone in classrooms with supply air at 65 degrees with displacement ventilation versus mixing supply air at 55 degrees. Naturally, it requires less energy to supply air at 65 degrees, and it opens much bigger windows for free ventilation with a 65 degrees supply temperature. Returning back to kitchens, again, thermal displacement ventilation allows to reduce temperature in the occupied zone by 5 to 10 degrees Fahrenheit. And exhaust hoods, because thermal displacement ventilation does not create any cross drafts, it allows hoods to operate at about 15% lower exhaust airflow rate compared to mixing systems, because you don't need to compensate for cross drafts in the space with thermal displacement ventilation. Do we have any questions?
Not at the moment. Again,
All right.
though, reminder, Chad,
All right.
if you do have any questions, please pop them in the chat and we will stop Dr. Livchak
All right.
and we'll keep asking.
Moving on.
Okay.
This is another application case for displacement ventilation. About several years ago, we were invited to one of the military facilities, one of the military bases where they repair helicopters, and it's a huge space in Corpus Christi, and it's huge space, not air conditioned, and people work only in small areas. As you can see here, people are actually working in this area, and the rest of the space is basically unoccupied. And as you know, Corpus Christi can be very hot in summer, and it would close down basically whenever space temperature reaches, as I recall, I think 95 degrees. We suggested to create kind of local cooling environment using, of course, cooled air and using displacement ventilation diffusers in combination with welding curtains. So this way we place the displacement diffuser in the upper part of the space. We're basically using curtains, just welding curtain, doesn't have to be airtight, to seal this area from the rest of the space, and manage to condition it with very minimal energy impact to condition this, to provide these local cooling conditions for people working in the small area. Another application that I already mentioned, schools, atriums with high solar load, high ceiling. These are beneficial applications for thermal displacement ventilation. We use displacement ventilation in retail facilities, again with high ceilings. Theaters and auditoriums. This is where displacement ventilation shines, especially supplying air through under the seats, because your ventilation rate is pretty high. You need a lot of air per person, and that's where you could also stratify heat and contaminants. We use it in industrial spaces as well. You can see displacement diffusers installed near the floor, and we use it in restaurants, as I mentioned before as well. Health clubs, commercial kitchens. It's been used also in smoking lounges, cafeterias, in the airport. This is a picture from Dallas Airport. Now about ASHRAE Standard 62 and displacement ventilation. As I mentioned, due to stratification effect of displacement ventilation and better air distribution effectiveness, displacement ventilation gets the credit in Standard 62.1 for better air distribution effectiveness compared to a mixed air distribution system. In other words, you need less outside air to provide the same condition in the space compared to mixing system. And this is table 6.4, 6-4, to where you can air distribution effectiveness for stratified system varies from 1.05 to 1.5. A lot of questions I'm getting actually, how displacement ventilation work in heating mode, what happens? First of all, as I mentioned, displacement ventilation works only in cooling mode, because to achieve this stratification effect, you need to have supply air temperature lower than space temperature. So displacement ventilation works only in cooling mode. And the moment we start supplying warmer air through displacement diffusers, it would start mixing with room air and rising into the upper part of the space. So in classrooms, we've seen a lot of applications. You could utilize still displacement ventilation with a secondary heating system, for example, using baseboard radiators to offset the skin losses, and still use displacement ventilation to provide fresh outside air. In that case, supply air still can be slightly lower temperature than room air, and then even in heating mode, when you have a secondary heating system, you can utilize stratification effect of displacement ventilation to still provide better indoor air quality in winter conditions. Again, when you start using displacement diffuser to supply warm air from displacement diffusers will start rising into the upper part of the space. And we conducted a comparison study in Finland with, as you know, in Finland we have pretty cold conditions. We used two types of system. We used mixing system, supplying air from the ceiling with a nozzle type diffusers that would blow warm air with high velocity into the occupied zone. And another option for heating was using displacement diffuser, supplying air at low velocity into the occupied zone as well. We found actually there is not much difference in temperature stratification in the room with both systems, because these diffusers, even though the air from diffuser rises, they started creating circulation zones in the space that allowed to mix warm air with room air with fairly high efficiency. And we found out that we need to use about the same supply temperature whether we use mixing system or displacement diffusers. So it worked in the same way as a mixing system as far as efficiency. But again, it's not displacement ventilation anymore. It's when you start supplying warm air through these displacement diffusers, it works in mixing mode. One way how to improve if you use thermal displacement ventilation as a primary heating system in winter, what you could do is to improve its efficiency to change the return from upper part of the space to the lower part of the space. That way you could improve effectiveness of air heating system when you use displacement diffusers to supply warm air. And in this case, in many instances, it can work better than air heating system using mixing diffusers. Again, so you will be using upper return in cooling mode and lower return in heating mode. When a lot of questions about what is the supply air temperature, typical supply air temperature with displacement ventilation in cooling mode. And when we talk classrooms or office spaces, because air is supplied directly in the occupied zone, it is recommended not to have supply air temperature not lower than 64, 65 degrees Fahrenheit. In this way, we cannot it prevents from drafts, and actually it satisfies thermal comfort conditions. But when we have our supply air temperature is 65 or 64 versus 55, how to get rid of humidity of air in humid conditions? For that, you could use hot gas reheat. You could also use return air bypass and use desiccant heat recovery wheels as well to get rid of humidity of outside air. Here I'm giving the summary of benefits and limitations of thermal displacement ventilation. Benefits of displacement ventilation is that it allows us to reduce energy consumption in most applications. It is a unique system because it's at the same time it is more energy efficient, but also it allows us to provide better indoor air quality with less energy. No drafts in the space, and it's most effective in spaces with high occupancy, classrooms, auditoriums, theaters. Displacement ventilation has its limitations as well. Typically, diffusers need to be placed in the occupied zone, so they take floor space. Diffusers are fairly bulky because you need to have fairly large air distribution area. And displacement ventilation should not be used when contaminants are heavier than air, because contaminants heavier than air that would not stratify. For example, parking garages with some particulate from car exhaust, that would be a bad application for displacement ventilation. All right, I think that's the end of the presentation. So I'm ready to answer any questions you have some.
Awesome. Thank you, Dr. Livchak. Chat, does anybody have any questions? Please feel free to put them into the dialogue box. We'll give everybody a couple minutes to ask anything that they may have as a follow-up. I did have one. I thought that was interesting. You talked about doing whether in cooling or heating mode, switching where the return was. Have you seen this implemented, and is this just done with a damper system and installing two return grills at the beginning, or how do you see this happening?
You could have like a column return with a damper inside. I haven't seen it done, but that would definitely be very beneficial and would expand application of displacement ventilation in cooling and heating mode. It's an idea that I'm sharing with the audience and everyone, but we haven't implemented it yet in practice.
Awesome. No, I thought that was extremely interesting on increasing the efficiency of some of that.
Yeah, and what it is, it's the efficiency would be better compared to all air supply, because when you supply warm air through ceiling diffusers, this air stays in the upper part of the space and doesn't circulate back. Yeah.
Right. That makes a ton of sense.
Yeah.
Thanks, Carmen. A reminder, please fill out the DL form, and then that way you can get your professional development credits. Nothing's coming through at the moment, so you must have explained it perfectly.
All right.
Well, we'll let everybody. Yeah, absolutely. Thanks for joining us. We'll let everybody go, and thanks for coming in for the discussion.
Thanks. Bye.